Okay, so let's continue with more examples. I will solve two more questions. So basically, the solutions will be very similar to each other. Then we will see an easier way to find complete sufficient statistics when the range of x not depend on theta case. So let x have the PDF. Okay, so this is given to us. So we have 3 theta cube x to the minus 4. The range of x depends on theta. Theta is positive. Here, okay, here the mean and the variance is given, but actually I think we will not use this information. And sigma square equals to 3 theta square over 4. Okay, part A. Actually, we can say that just find minimum variance unbiased estimator of theta. Okay, but this question asked as the steps of the finding complete sufficient statistic and then finding a minimum variance unbiased estimator of theta, actually not theta, minimum variance unbiased estimator of mu. Okay, so find a sufficient statistic for theta. So this is our first step. So we find sufficient statistic first, which has all the information to estimate theta. Then we will show that it's also a complete sufficient statistic. And then find the apply Lemma-Scheffer theorem to find the minimum variance unbiased estimator. Okay, so let's find likelihood function to use Nameless factorization theorem. So 3n theta to the 3n and then multiplication of xi values I from 1 to n, each xi greater than or equal to theta. Okay, so here in the form of the PDF, we have only theta terms, so these are in multiplication terms, so we don't have a statistic inside. But when we look at the range depends on theta. So again, we are using the same logic. If which statistic is given to me, then the lower bound of x is independent of theta. Okay, so in this case, what we are doing, again writing this in order statistics form, and then see that the minimum value is the first order statistic. So if this is given to me, then I don't need to know what is theta. Okay, so this should be my sufficient statistic. But to be able to apply Lemma-Scheffer, Nameless factorization theorem, I need to put this information inside of the likelihood function and create K1 and K2 functions. Okay, so how can we do that? So we have a function of theta. So let's add an indicator function. Okay, and then state that the first order statistic x1 is between theta and infinity. And then the nth order statistic is between is actually less than infinity. Okay, 0 to infinity. Okay, so combining the ranges for x1 and xn basically will give us the range of xi. Okay, so then we have 3 to the n multiplication of xi to the minus 4i from 1 to n. So we created two functions. This part is a function of, this part will be k1, function of a statistic, first order statistic and a parameter. The second part, this part is k2, okay, xn, not function of theta. So we can write our PDF in Nameless factorization theorem form. So by the Nameless factorization theorem, x1 is a sufficient statistic for theta. So part B, show that y is a so y is this one actually, or show that so let's say this is y. Show that y is a complete sufficient statistic for theta. Okay, so at this point we need to find the PDF of y. Okay, PDF of the first order statistic. We cannot use this given PDF. Okay, so be careful about that. Usually you are doing this mistake at this point. So you are showing that x1 is sufficient statistic, but then in the expectation calculation you are using the given PDF, not find the PDF of the first order statistic. Okay, so first of all we need to show that expected ux1 is 0 for all theta requires that ux1 itself is 0 for the case that x1 value for all x1 greater than theta. Okay, so we need to show that. So what is this? Okay, so we have a continuous random variable and the lower bound is theta, so ux1, and then find the PDF of first order statistic here, dx1, and then equate it to 0 and then try to show this. Okay, so we need this. So what is this? So we need to have the CDF first to calculate to find the PDF of the first order statistic. So theta to x 3 theta cube x to the minus 4 dx. So we get this one as the CDF, x greater than or equal to theta. Don't forget to write the range. Okay, so then the PDF of the first order statistic here is n times the PDF and then 1 minus f of x1 to the n minus 1. Okay, so n, so 3 theta cube x1 to the minus 4, so 1 minus theta, so 1 minus 1 plus theta cube x to the minus 3 to the n minus 1. So when we combine them, we get the PDF as 3n theta cube 3n. Okay, and then we have x1 to the power minus 3n minus 1. What is the range? Range is this one. Okay, so then after finding this, let's show the completeness. Okay, so get the expectation formula ux1. So for any arbitrary function of x, ux. So let's put in a parenthesis. Okay, so from 0 to theta. Sorry, not 0 to theta. Oops. From theta to infinity, ux1, and the PDF of xn. So we have n theta to the 3n, x1 to this one, dx1 equated to 0. So at this point, so this is 0 for all possible values of theta. So get rid of all constants and theta part. So that we are integrating with respect to x1 and this is an equality to 0. So just get rid of this part. Okay? So we divide everything by 3n theta to the 3n. So what we have here is from theta to infinity ux1 and then x1 to the minus 3n minus 1 dx1. Okay, so all the calculations will be very easy if you get rid of this part. Okay, otherwise in the when we are using Leibniz rule, so there will be in the partial derivative there will be theta, so you have to also work on that one. So to ease the calculations, it is necessary to do the step, get rid of the constants and the parameters here. Okay, then since if this integral is 0, then its derivative also is 0. Okay, so our logic is this one. And basically we want to show that ux function itself is 0. So by taking the derivative of the integral, so we can get that one. Okay, so then to be able to do that, we are using Leibniz rule. Okay, so what was that? Then we are putting infinity, taking the derivative of the infinity. So first part is 0. So minus, put the theta for the x terms. Theta to the 3 minus 1. And then take the derivative of 1, which is just, take the derivative of theta, which is just 1, plus theta to infinity. Take the partial derivative of this one, minus 3 and minus 1, x1, this should be theta, partial derivative. This should be x1. So since the terms that we have here we don't have any theta term here, this term is 0. Okay, then what we have? Okay, so minus theta to the minus 3 and minus 1. So this should be 0 for all possible values of theta. So this part cannot be 0 because it's positive. So what we have here is u theta is 0 for all possible values of theta. Actually, if you remember at the beginning, u is an arbitrary function of x. So just replace theta by x because it's a function of x actually. So ux is 0, theta x greater than 0. So then what is the actual range of x? Then write that one. So ux is 0 for x greater than or equal to theta. So basically this is inside but not more narrower range. So basically we showed that expected ux is 0 if and only if, actually this should be x1. And only function itself is 0. So this means that y, or the first order statistic, is a complete sufficient statistic for theta. Okay, then see, find the minimum variance unbiased estimator. Minimum variance unbiased estimator of mu equals 3 theta over 2. Actually, we can find first minimum variance unbiased estimator of theta, then the function of that, but function of that is just multiplication of 3 over 2, so the calculation will be easy. Okay, so here at this kind of parts, remember the Lemma-Scheffer theorem. Lemma-Scheffer theorem tells us that when you have a complete sufficient statistic, if you can find a function of complete sufficient statistic which is an unbiased estimator of the parameter, then it will be the minimum variance unbiased estimator. Okay, so then our starting point should be expectation of complete sufficient statistic here for theta, whatever that function actually here is. So basically here mu is just a function of theta. So we can start with theta. If it is theta squared, then we can think about the variance or other things. But start with that. Okay, so see what's the form of this one. So it will give us theta or other things. Okay, so what is the first order statistic? Is the complete sufficient statistic. So let's find this one and see what is the form of that. Okay, so from theta to infinity, x1, and then write the PDF of the first order statistic here. x1 minus 3 and minus 1 dx1. Okay, so at the end, when you do these calculations, you will get 3 and minus 1 theta. So it's a function of theta. So I can definitely find the minimum variance unbiased estimator of theta very easily. But I want to find the minimum variance unbiased estimator of 3 theta over 2. So it will be much more easier. So I had this part, 3 theta part. Okay, then I need over 2 part, and I need to get rid of 3 and minus 1 and n part. So what I'm doing here. So multiply both sides by 3n minus 1 over n. Okay, and I need 1, 2 here. So x1 over 2. If I do that, I will get 3 theta over 2. Okay, now this is a complete sufficient statistic. So in terms of complete sufficient statistic, I found the unbiased estimator of 3 theta over 2. So by Lehmann-Scheffel theorem, this quantity 3n minus 1 over 2n x1 is the minimum variance unbiased estimator of mu. Okay. Okay, one more part here. D. Find the minimum variance unbiased estimator of sigma square. Actually, let me stop here. Let me tell you something actually. So, for many cases actually, for unknown parameters, what we are using, or for many cases for mu, population mean, what we are using is sample mean, right? But actually, for this case, we are seeing that sample mean will not give us the best estimator. If our sample is coming from this distribution, okay, so distribution with this PDF. Where is it? Somewhere here. Okay, so with this one actually. So this means that I cannot use sample mean to be able to represent the population mean. Which one should I use? At least I have to find the minimum value, first order statistic. And then I have to use this 3n minus 1 over 2n first order statistic to be able to estimate population mean, mu. Okay, so this doesn't mean that, so this actually shows us that we cannot always use sample mean to be able to estimate the population mean. Okay, so for different samples or for different PDFs or different distributions, we have different representatives of the estimators of the parameters. Okay, so the fourth part of the question is find the minimum variance unbiased estimator for the variance sigma square. What is sigma square? It is 3 theta square over 4. So here you have to do this type of logic. So with the first order statistic, expectation of the first order statistic, I get a function of theta. Then by using the square of that expectation, I probably get a function of theta square. Okay, so you have to think like that and then find the expectation of x1 square. So to theta to the infinity, just take the expectation of the first order statistic and then PDF of the first order statistic. dx1. Okay, so what is this after the calculations? I skip the calculation part. 3n over 3n plus 2 theta square. Okay, so as I guess, it's the function of theta square, but you have to do and then see the form. So main logic is this one. Okay, so first of all, find the complete sufficient statistic and then take the expectation of the complete sufficient statistic and then see what's the form of the expectation. Is it a function of theta? Is it a function of 1 over theta? Is it a function of ln theta? Whatever that is. Okay, after seeing that, then you have to think about, okay, so if it is theta, that's okay, then I can get the unbiased estimator using that complete sufficient statistic. Or if it is square like this case, okay, then I have to, by using x1 I get theta, then I have to use x1 square to get theta square. Okay, so you have to think about such kind of logic and then try to find the unbiased estimators of the parameters based on this. Okay, so then okay, so I need to find the 3 theta square over 4. Actually here I had again 3 part, so I need over 4. Okay, so expected 3n plus 2 over n part is okay. So this is also in the expectation. I need over 4, then I will get 3 theta square over 4, which will be sigma square. Okay, so now x1 is the complete sufficient statistic for theta. Okay, then using the complete sufficient statistic of theta, then I find a function of complete sufficient statistic which is an unbiased estimator of the parameter that I want. So again, by using the Lemma-Scheffer theorem, I can say that this one is the minimum variance unbiased estimator of sigma square. As you can see here, also usually what we are saying, sample variance is the estimator for the population variance, but for this example it's not true. So if you use sample variance formula, you will not get the best estimator to represent the population variance. If you use this formula, okay, so you will get the best estimator. So when you have a sample, get the sample size, get the minimum value, take the square and calculate this quantity, then it will be the numeric representation estimate of the sigma square. Okay, so this actually shows us why we are doing such a thing, actually, why we are not using just x bar for the population mean, not just using s square to be able to estimate sigma square. So we need to see for which distribution what are the estimators of the true parameters. Okay, so let me stop here. I will solve one more question, okay, and then I will stop today. Okay, we have next week we will see exponential class of PDF. Since you said that I'm going too fast, I will be a bit slower. Okay, so see you on the next video with another example.